The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's Online CEU Program, depending on their content. You can earn continuing education credits through ACI's Online CEU Program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
At this time, I would like to introduce our next speaker. It'll be Norbert Delatte. Norb is going to talk to us about case studies with internal curing in bridges in the greater Cleveland area. Norb is professor and chair at the Department of Civil and Environmental Engineering at Cleveland State. He's got a bachelor's of civil engineering from the Citadel, master's from MIT, and a PhD from UT Austin. He's won the ACI Bloom Award and the Walter P. Moore Award for faculty achievement. He's a fellow of ACI and ASCE. He's a registered professional engineer in Ohio, Alabama, Virginia, and probably several other states. No, that's it? Okay. And is a veteran of 11 years on active duty with the U.S. Corps of Engineers. So without further ado, I'll ask Norb to tell us about what's happening in greater Cleveland as I pull up his slides.
Great. Thank you very much. Talk about the greater Cleveland area rather than the city of Cleveland because a couple of these are outside of Cleveland, and it really means Cuyahoga County, and more specifically ODOT District 12, which is pretty much Cuyahoga County. My co-author is a concrete engineer from ODOT District 12 who is shortly going to be retiring from ODOT, so if by any chance you're looking for a really good concrete guy with a lot of state DOT experience, I'd be glad to put you in touch with Dale. It's kind of unfortunately, he's helped me get 2 very interesting research projects, and I'm going to hate to see him go. But anyway, we're going to talk about a couple of approaches, and actually the third approach, some of these are mentioned, the third approach I'm almost going to say wasn't really an approach to internal curing. It's kind of sort of the dumb luck thing you wander into. But the different approaches are one, looking at different levels of absorption of your coarse aggregate. The other one is what we define lightweight aggregate replacement, addition into concrete. And the final one was the use of a lightweight concrete, actually a sand lightweight concrete that happened to use tight case cement. So the genesis of this study and where I got the research project from ODOT is 2 engineers from District 12, Dale Crowl and Mike Sutak, undertook a survey of high-performance concrete bridge decks. And what they found in their survey was that the early age cracking of bridge decks was increasing, and they tried to find out why. Essentially, this is what happened in ODOT District 12. Between 1994 and 1996, they built approximately 30 bridge decks, and only one of those showed any substantial cracking. Then they switched to high-performance concrete, starting in 1997. Between 1997 and 2001, 79 bridge decks were built, and 48 of those showed cracking, which leads one to wonder what sort of high performance we're getting out of that. So it was a big change, and they wanted to figure out why. And so what they did, which I really liked, is they started looking at what were, for these 79 bridges, what was the common factor between those that cracked and those that did not crack. And the nice thing about bridges is you can walk around under them and look up generally and see whether or not there are cracks. And the first speaker actually had the picture on the right, and he only had 3 of my slides, so most of those are new, 3 of the pictures. But standard mixture, the only thing that changed when they started looking at it is the one on the left that had, and they also look at size ASTM 57 and number 8 coarse aggregate, is that those all had absorption capacity well under 1%, and those bridges tend to have some pretty bad cracking. On the other hand, bridges that did not crack looked like they had absorption capacity in the 2.5% and 3% range. And this theory was probably best illustrated or best confirmed in a project that had staged construction. So you had the same bridge, you had the same contractor working on the bridge, and half of it cracked and the other half did not. So what changed? You got the same contractor, you got the same mixture proportions, same phase. However, the concrete plan had changed the source of the coarse aggregate in between those two phases of construction. And so the side that cracked had a relatively low coarse absorption, and the side that did not crack had about 1.5%. So on the basis of this information, ODOT District 12 made a number of adjustments, all of which to me made sense. They decided rather than using just one aggregate, they would try for more to fill in the structure, use a blend of 57 and 8. And when you do that, with a denser aggregate structure, you can reduce your water and your cementitious materials content, and you don't have to change your water cement ratio. And they changed their specification to only allow medium and high absorption aggregates. So they changed the specification pretty much. You could not use less than a 1% high absorption aggregate. In the new design, they had a slight increase in the water cementitious materials ratio. Well, it's good engineering, but not very good research, because they fixed their problem, and from a research standpoint, they really didn't care. In terms of trying to figure out what the issue was, you changed 4 variables at the same time, your problem went away, but you don't really know which variable that you changed that actually did that. So Cleveland State then was brought in as researchers to try to look at this in the laboratory. We already had it. It's kind of interesting. It's sort of backwards. Usually you do stuff in the laboratory, and then you go out and you look and see if you can replicate it in the field. Here we had some field observations, and we were sort of trying to back calculate things from the laboratory. And so we got some supplies of aggregates that were commonly used by ODOT, different sources, a low absorption, which is less than 1%, what we defined as medium absorption between 1 and 2, and then we had a material that was relatively high absorption. In Northeast Ohio, they primarily used crushed limestone. The state wanted to look at this in a broader sense, and in other parts of the state, they use river gravel. We could only find one with a medium absorption. And we did a number of ring tests, and sometimes looking at the time of cracking and so forth, and sometimes in the duplicate rings the cracks occurred together, and sometimes not so much. We crunched all the numbers and looked in terms of cracking potential. The nice thing about this is at this time, BASF out in Beechwood was doing a number of ring tests, and so they helped us with both setting up the test and some literature on how to interpret the results. The problem is a lot of these tests are done on mortars because you get results much more quickly. And you use relatively thin rings. If you want to try to test a 57 stone, you can't really use a thin ring. You have to go to a much larger ring. It means you need to wait longer. The results become a whole lot confounding, so we try to make sense out of that. We tried to look at, though, whether our potential for cracking based on time of cracking and the stress rate of cracking was high, moderate, low, or low. And when we put together all of the numbers, what we found is when we looked at the basic high-performance mix, as expected, the low absorption concrete cracked relatively early, and the moderate medium absorption tended to take a good while longer. One thing that was kind of surprising was that the high absorption aggregates actually also had pretty early cracking time. And as near as I can figure that out, I don't think that the field sample from ODOT had many of these. And I think also when you get into those aggregates that have high absorption, they may have weaker tensile strength. And so when you look at cracking, you're basically looking at stress. Stress is chasing the strength, and so even if the stress isn't all that high, if the strength is also low, you don't go anywhere. But what we did find is that when you included the lightweight aggregate, you generally can bump up about a category. You generally improve your properties. So we decided that we thought that looking at the data across the board is that adding the lightweight aggregate, regardless of your original cracking tendency, tended to make that concrete more resistant to cracking. The problem we had is we looked at 16 and 18-inch rings, and we used a correction factor for the 18-inch rings, and when you go to an 18-inch diameter ring, it is a relatively thick donut of concrete. It's quite frankly kind of hard to get it to crack. The blending of the aggregates did help a lot in improving the resistance, and obviously, if you have a number 8 top size aggregate, which means you have more paste, you have a greater risk of cracking. So the question came up, all right, now that we've done this laboratory work, how does it translate out in the field? And one thing I like to have, of course, is very large test specimens. That's Dale Crowl on the right, by the way, and my graduate student at the time, John Cleary, is now on the faculty down at University of South Alabama. And so we had a new bridge going up in Willoughby Hills, which is on the east side of Cleveland, and we did 1/2 in the conventional ODOT modified mix to make sure that Dale had switched to what the rest of the state calls the Crowl concrete mix. And then we took the other one and we added some lightweight aggregate to see how they would do. So basically, in words, one side was a modified mixture using a blended aggregate. The other side, we added the lightweight aggregate. Both mixtures were pumped. Now, obviously, ODOT has no interest in whatsoever in having a bridge deck crack simply to prove my point. And so we basically took a crack-resistant mixture, another one that was even more crack-resistant, and we really did not see much in the way of cracking. In fact, I'm not even sure we saw any at all. Their HP bridge deck mixture is really designed on a durability, permeability type basis. Their compressive strength, required compressive strength is 4,500 psi, and they routinely blow by that by 2,000 to 3,000 psi, which really isn't all that relevant for a bridge deck because how many times have you seen a bridge deck fail in compression? It's always durability issues that get it one way or the other. So that is some pictures we took in the casting of the full-scale bridge deck. And then we had a small crack. We think there may be a small crack that showed up at about 5 weeks, but didn't seem to, that could almost be an artifact of the light. So Dale and I put in the abstract for this, and then we realized at some point that, wait, the paper's due. Maybe we should go out and take another look at the bridge. I think you've seen that slide already. I don't remember right now which side is which on this, but neither one of them cracked, at least as you can tell without risking your life and getting way out into Interstate 90. So all in all, that bridge is working pretty well from the material curing standpoint. The final one I want to talk about, and this has actually been mentioned earlier by the late Bob Gulyas of BASF, and Bob gave me a copy of his paper and a whole bunch of slides, and he says, you know what, you really need to go to ODOT and get some money into a research project on this. We need to figure out why this bridge worked as well as it did, and unfortunately it's something I never quite got around to doing. So he wrote a paper in 2008 for a conference which was entitled High Performance Bridge Deck Use of ASTM C845 Type K Shrinkage Compensating Cement with Lightweight Aggregate to make good concrete. I'm not going to go on with the rest of it. Very long title. The Main Avenue Bridge is in downtown Cleveland across the Cuyahoga River. It was redecked in 1992. It was redecked using a sand lightweight concrete deck. Now, my understanding of the bridge is that this was not done for any purposes of internal curing. The redecking of the sand lightweight concrete deck was to allow you to reduce the dead load so you could add traffic in each direction without having to strengthen the bridge. My understanding, I think I've read some recent articles that we have some concern about the capacity of this bridge, but all from the steel understructure of the bridge. So the materials passed on to me from Bob. The concrete mixture was about 715 pounds per cubic yard Type K cement. there was in the expansive concrete, I think it was called session yesterday afternoon, they talked about this bridge in Bob's paper, this presentation, and also between 1985 and 1990, ODOT, and I think the entire turnpike continues with this, built more than 300 bridge decks with tight case cement. And those seem to work pretty well. So considering that they've gone probably a couple decades without any serious bridge deck cracking problems, you can see why they're even more concerned when they switched to HPC and had these problems. The coarse aggregate was 3/4 inch lightweight aggregate, air, relatively high water cementitious ratio of 0.55 with a fair amount of tight case cement. Bob Gulyas took this photo of the underside of the bridge and reported on that in his paper in 2008. At that point, the bridge deck had been in service for about 15 years. Let me point out one thing about the location of this bridge. Cleveland has the greater Cleveland area has a wonderful combination of lots of bridges and some really nasty climate conditions in freeze-thaw. If you want a place to do bridge durability experiments, you can hardly come up with a better place than Cleveland. And this particular bridge is actually pretty close to Lake Erie, and so we get a lot of the storms that blow in off of there. So after 15 years, I do see a lot of concrete deterioration in Cleveland. It's a great place to take classes for field trips about what sort of problems you can have. And after 15 years, excellent condition, no cracking. Most of it, unfortunately, has, well, stay-in-place forms, so there aren't that many places you can look at it from underside. Dale and I went around, we took a look, and pretty much ended up the same place that Bob had been able to take his photos. So, with the paper due, Dale and I got in the ODOT vehicle and continue on out to this one, and the bridge deck is still in excellent condition. There's no cracking, spalling, no issues with freeze-thaw damage, no scaling. What's interesting is you can almost tell where this starts by the deterioration from the approaches, because you go out these approaches, which are conventional concrete. Now they may be older, but they are all chewed up. They have all these problems you'd expect to find in this area. And then you get on the bridge deck and it looks great. And then you get off and you're on the approaches and those don't look so good either. And even in December, which is relatively early in our season, we had little accumulated piles of road salt already on the edges of this. So you know that this bridge is subjected to just a ton of salt. Cleveland, by the way, has a salt mine under it, Cargill salt mine, so we don't have to take it very far. We just take it straight up to the mine and right on the road. And it eats concrete, it eats steel, it eats everything. So basically, these are my conclusions. I agree with many other people that say that internal curing is effective. We have seen some variation in the absorption of the aggregates that can be helpful in some cases. I kind of, when I finished my study, almost had as many questions as I started with. But our lab studies confirmed the field results that, and I think they didn't see the problem with higher absorption because they just didn't routinely use those materials. Our full deck bridge test is only 4 years old, still in great condition, but if there were problems, they would show up later. The Main Avenue Bridge with the tight case cement is in excellent condition now after 20 years in a part of the world where concrete shows its age very, very quickly. So I think there is a lot of potential to look at some of these expansive and shrinkage compensating concretes combined with the lightweight aggregates and see if you can deal with some issues. We haven't really looked at the effect on freeze-thaw. I understand other people have in terms of fatigue, wear resistance, and permeability. And I really think a place that we could make a lot of use out of internal curing is thin overlays on both bridge decks and on pavements that are known to be problematic from the standpoint of delaminations. Those of you who were at the TAC breakfast may remember Blake talking about the new repair code and the problem that most repairs only last about 5 years. And a thin overlay is a very big repair, and we don't have the world's best reliability history with those. In terms of the acknowledgements of the original ODOT study, of course, John Roberts, Northeast Sunlight provided all the material for that test bridge, had a number of graduate students, and I do, of course, want to thank the late Bob Gulyas. I asked his colleague for a picture of him. He actually passed away just before the Pittsburgh Convention, October 2010. This is sort of the expression he generally had when he was getting ready to set some professor straight who had sort of wandered from the correct path, if you knew Bob, but kind of sorry I can't follow this up with him anymore. So, but he did provide some good information and some impetus in looking into that bridge. And you know, we do a decent job of studying our failures. We tend not to do that good a job of studying our successes. And if we built things that perform very well, I think those deserve just as much of a forensic investigation so we know what we're doing right and so we can replicate it, and so we don't change the specification and go from a situation where we have maybe one bridge and 30 cracking until all of a sudden over half of them crack in the process of improving what we're trying to do. So I'd probably beat that point to death, and I'll leave you with the photo of Dale Crowl and my favorite label on the testing machine from the lab. So I'll take any questions you may have.
Thank you very much, Nick. Very interesting. We've got time for some questions.
All those differences in cracks, the early 90s versus late 90s, one versus
Yeah.
Did you happen to notice any difference in the grinds of the cement?
No, the guys who were doing, I don't know if there were any significant changes in that time, but that's not something that ODOT would have in its records. They would have, meets AASHTO spec, doesn't meet AASHTO spec. What they did have was, when they changed the mixture, they have a very good database of absorption of all their aggregates, so they wouldn't have had that information available. That's a good question. Now, the thing about concrete, it's a very, very simple material until you spend any time at all looking at it, and then all of a sudden you've got variables all over the place. They're very hard to track and control.
What was in their high-performance mix? You indicated that they got a lot more cracking in their high-performance mixes. Maybe you should go back to your own mixes.
That's a potential option. The HPs in ODOT are ternary blends. So it's cement, either slag or fly ash and silicon. And if I recall correctly, I don't have it with me, it's a fairly high cementitious content. So it really designed, the way it was explained to me, it was designed for coulomps in the RCPT. But as we pointed out, if you have cracks, it doesn't matter how low permeability the concrete in between cracks are. If you need red cracking, that takes care of maybe all the problems.
Isn't Bob Gulyas the one that said concrete is impermeable until it cracks?
You might have. He said all bunch. Question back there?
Yeah, you talk about thin overlay. How thin are you talking?
Standard bridge deck and even some pavement overlays on CRC in Texas, those can be 2-3 inches. And now, sometimes they use latex modified overlays, which are fairly expensive, but I think that the record has shown that plain concrete can work pretty well, but you really have the issue of possibly losing bond. And so I think you have the issue of differential shrinkage between the overlay and the base, and you have the issue of promoting bond at the interface. In my opinion, without having done a research project to prove all that stuff, I would think internal curing could improve both of those. But you'd have to do maybe some lab tension tests and maybe some field sections to verify that. It's just one place I would think. And the other thing is whenever you're doing an overlay, at least on a bridge, just like they were in the Main Avenue Bridge, you're worried about dead weight. So you can save a little on the dead load at the same time. But it's just a suggestion. If anybody wants to fund it, I'll be glad to try to figure it out. We'll work for money or food or whatever. Any other questions? Okay. Without any, Norbert, thank you once again for very, very interesting.